Okay, good morning. So let us continue. If you remember last time, I started talking about the Pascal identity, but we didn't finish that. So the Pascal identity is a very famous identity in the topic of combinatorics. So let me write Pascal is the mathematician and physicist, yes. I think it should be 17th or 18th century, I'm not sure about that. But the identity is this. So n choose r, the number of ways that I can choose are objects out of n distinct objects in a way that order does not matter to me. If you remember, that number represents that. This is equal to n minus 1 choose r minus 1 plus n minus 1 r. This is the Pascal identity. So if you have one of these coefficients, you can break it up into two pieces, or if you have two pieces of them in exactly this way, meaning that these numbers on top are the same, these numbers differ exactly by one. If you want to, you can combine them into one of these one single one of them, in a way that this number is one unit more than this, and this number is the bigger one between them. So for example, if I tell you 3 and, so let me make it bigger. So let me write 7 and 3. And if I ask you add this 7, 3 to 7 and 4, this is exactly of this pattern, yes? The numbers on top are the same. The numbers below differ by 1 unit. So if we prove Pascal's identity, then if I want, I can write it as what? One piece, yes? How should I write the one on the piece? This number on top should be 1 unit more than this common number on top, which is 8. And between 3 and 4, between r and r minus 1, I choose r. So between 3 and 4, I choose 4. So for example, this is one consequence of Pascal identity. If we know why this is true, if in case we need, we can combine them and write them like this, okay? So we want to prove this Pascal identity. This is a problem in the book. We can prove it algebraically, or we can prove it by storytelling. Okay, both of them are good. So let us just do them one by one. So first, algebraically. Algebraically shouldn't be any problem. So you want to prove an identity using algebraic method. So you start from the side which is more complicated and try to simplify it as you go on and reach to the other side. So here, this is more complicated. So if you don't mind, let me start from the right-hand side and try to simplify it. And of course, this formula is already derived. We know that if I have, for example, let me write capital N and capital R. N choose R is n factorial. If you remember, we derived this before. R factorial multiplied by the difference between these two number factorial. So I want to use this formula that we derived before to simplify the right-hand side and reach to the left-hand side. Okay, so how should I do that? Here, I compare this with the formula. N minus 1 is playing the role of n. R minus 1 is playing the role of r. So I substitute these into that formula. So it becomes n minus 1 factorial divided by r minus 1 factorial multiplied by the difference between them factorial. So what is the difference between them? N minus 1 minus r minus 1. So this becomes n minus 1 minus r plus 1. And this one and that one are gone, so it is just n minus r factorial. Yes? And then I go to the next one. The next one, n minus 1 plays the role of capital N, but little r plays the role of capital R. So I just substitute it there. So it becomes n minus 1 factorial again, divided by this time r factorial, the difference between them, n minus 1 minus the one below factorial. Yes? This is just the expansion based on the formula we had. And then I have to find the common denominator. Why? Because I see that the right-hand side consists of two terms, the left-hand side consists only one term, so it motivates me to combine them if possible. So I have to find the common denominator. But of course, naive common denominator is to multiply everything, so it makes life hard. So we need to see that what is the optimal way of finding the common denominator. In other words, I want to find the least common multiple between these two. So how can I imagine this? R factorial includes r minus 1 factorial as a factor. Why? Because r factorial can be viewed as r times r minus 1 factorial. So between r factorial and r minus 1 factorial, r factorial works fine because it not only includes itself but also includes r minus 1 factorial as a factor. Now here this can be written as n minus r multiplied by the number previous to this factorial. The number previous to this is 1 unit less. So it is n minus r minus 1 factorial. And now you realize n minus r factorial is not only good for itself, but it is also good for this term because n minus r minus 1 is exactly as n minus 1 minus r. There is no difference. So can you tell me what is at the end the common denominator by this analysis that I just presented? Yes? Yes. R factorial is good for this one and that one. N minus r factorial is good for itself and that one. So that is enough. I don't need more than that. Okay? And now I compare this with what I have. R factorial with respect to this has an extra factor of r. Yes? But n minus r factorial is exactly as n minus r factorial. So if I say that what extra factor I have when I compare this denominator with that denominator, there is only a factor of r. So I have to multiply the corresponding numerator by that extra factor. So it becomes r times that. So if you don't mind, let me write it n minus 1 factorial times r. And then addition. And then I do the same thing. I compare this common denominator with the second denominator. R factorial and r factorial are exactly the same. So if I compare n minus r factorial with this one, because of what you see here, what extra factor I have? I have n minus r as extra factor. So I have to take that extra factor and multiply it in the numerator. So it becomes what? N minus 1 factorial, which is already in the numerator. My rescaling factor is n minus r. Yes? But now what happens? The denominator, I just copy and paste it. But in the numerator, n minus 1 factorial appears as a factor here and appears as a factor there, so I can pull it out. So it becomes n minus 1 factorial, and then I open a pair of brackets. What is left from here are addition here plus, and I pull this out. What is left is n minus r. Yes? But then extremely simple. Now you see this minus r and that r are gone. So it becomes n minus 1 factorial multiplied by n divided by the denominator is r factorial n minus r factorial. Yes? But can I combine these two? Yes. N minus 1 factorial means multiplication from 1 up to n minus 1, and then I am multiplying by n. So if I combine them, it simply becomes n factorial divided by r factorial n minus r factorial. But if I ask you what do you see now on the board, that's exactly this formula unless capital N is replaced by little n and capital R is replaced by little r. So this is nothing except n choose r, and that is exactly equal to the left-hand side. Yes, so I was able to reach from the right-hand side, do some algebraic calculations, and reach to the other side. So that the proof is simple. But what about the story proof for this? Can you come up with a story in which solving that story problem in two different ways convinces us that this equality should hold? So you have already an indication here. So what's the good story for the left side? You have n students, you want to choose r of them, for example. Yes. So that is a good story, because when you see this on the left, You need to come up with a story like this. You can say that I have n distinct marbles, I want to choose r of them, or I have marbles are not good because it tells you that might be you rearrange them, it becomes a new. But if I have n people and I want to choose r of them, this is the way, this is the number of ways that I can do it in that way. But how can I come up with the second version of the story that shows me that these two should be the same? Okay, so let me write. We have a student 1, student 2, student 3, up to student n. Let me write student n minus 1, student sn. These are the students I have. I want to see in how many ways I can choose r of them and take them with me, I don't know, to cinema, for example. Okay? So in how many ways I can do that? This is the standard, extremely standard problem. That's the number. Yes? So it becomes, I have n people, I want to choose r of them, and the order does not matter. I want to take them with me to the cinema. So this is the number of ways that I can do it. Okay, this is one version of the story. Another version of the story is, let us, for example, concentrate on the last person. Either that last person is in my choice, I take that person with me, or I don't take that person with me. There's no other choices, yes? And then I consider both of them and add them up. So it should give me exactly the same number of ways, yes? Do you agree? So let us say that in my choices, I have two options if I want to. Either I choose the last person to take it with me. Okay, now let us solve this problem. In how many ways I can choose r people, but I insist to have this last person in my choice. I want to choose r people, r students, but I insist the last student should be in my list. N minus 1, r minus 1, is that right? Yes, because if I insist that Sn should be my list, in total I am supposed to choose r people, but if I insist to have Sn, it means that I already decided about one person. So how many other choices I want to make? R minus 1, but among for how many people left? N minus 1. So this becomes n minus 1 choose r minus 1. If someone asks you what is this, this is the number of ways that I can choose r people from n people, but Sn is in my choice. But now let us say that how many of these choices I have in which Sn is not in my choice. Okay? Or, because if I insist not to take that person with me and I still want to choose r people, then I choose r people from n minus 1 left people. Yes? So this number becomes n minus 1 r. So either I choose that person or I don't choose that person. The number of ways that I can choose that person is this. The number of ways that I don't choose that person is this. So in total, in these many ways, I can choose that group of R people. But these two should be the same because I am counting the same thing in two different ways. Is that right? So this is a good proof, and that was simple, but this is a nice idea. Any questions here? Okay. So let us try to do some algebra here. So this formula, I don't know if it's in the formula sheet or not, but if I want, I will check it out. But if I want to give a questions and it's not in the formula sheet, I will write it for you in the question itself. But let us say that I have this on the board. Can I simplify this a little bit? So it's a multiple choice question. So let me write 10, 3, let me see, 10, 3, 10 choose 3 plus 2 times 10 choose, what is that? 10 choose 4 plus 10 choose 5. Okay, so it's a multiple choice question. I ask you what this is, and I am offering you 4 options, okay? 2, 3, and 4. So the first option is 12, 5. 12 choose 5. The second option is 12 choose 6. The third option is 11 choose 6. And the next one is 10 choose 6. Of course, let us say that you don't have calculator available. So how do you think we can solve this problem? Of course, this is an example. I am just telling you after talking about the Pascal identity, so it should be related to that. In principle, this is not a hard problem, yes? Because, for example, you can be patient and calculate this, calculate this, calculate this using that red formula. And then you get a number. Then start to calculate these things to see which one fixes that. That is in principle, but it's not efficient. If the numbers are big, and if you want to do it like that, it doesn't work. Yes? No, just tell me what to do first. Yeah, so you are breaking the middle one into two parts, yes? So that's not hard, you see? So this question mark is equal to, I copy and paste this part, but this is 2 times this number, so I break it into 2 parts. So one of them plus another of the same one, yes? These 2 numbers added becomes 2 times the same number, but you might say, what is the benefit of doing that? Then immediately you see that this is a Pascal identity. That is also another Pascal identity, yes? Why is that? Because in the Pascal identity, I have 2 of them. The top numbers are the same. The bottom numbers differ by 1 unit. And then if this happens, I can combine them in this way. So do you think that I can combine them in which way? You see, the top numbers are the same. The bottom numbers differ by 1. So if I want to combine them using the Pascal identity, what should I write on top? This number on top is 1 unit more than this common number on top. So if this is 10, it becomes 11. And the number in the bottom is is the maximum one, because there is r minus 1, there is r, which one I choose? The bigger one. So between these two, which one I choose? 4. Yes? And I will do the same thing here. It's also in a Pascal identity, yes? What is the answer? This becomes 11, but which one I choose? 5. Then I have to add them up. But this is also another Pascal identity now. Why? Because it has the same pattern. I have 2 of them. The top numbers are the same. The bottom numbers differ by 1. So I can combine them as to write it what? The top number should be 1 unit more, which is 12. And between 4 and 5, I choose what? 5. Okay. So this is in the list. So this is the answer. Okay. Might be they don't put this directly in the answer. They might put this in the answer. Do you agree that these two are the same? This is also very important to remember, yes? Here, I want to choose 5 people from 12 people, take them with me to the cinema. This is the natural way humans do it. They read the list of the people who are taking, but I can also read the list of the people I don't want to take it with me. So you remember, this is a very important rule. We have discussed about this before. So this is equal to n minus r. So for example, if I have 90, 81, this is exactly equal to 90, which what? 9. As soon as these two numbers add up to the number on top, these are the same. Okay, but of course this was not that hard, so this is in the choices, so that I will choose this one. Yes, is that okay? So what about this one, for example? This is a little bit more tricky, but that's also simple. So I have 2, 2, 2 choose 2, and then I have 3 choose 2, and then I have 4 choose 2. Let me see if I'm writing it right. Yes, and then up to 99, 2. 99 choose 2. So what do you think the answer to this will be? I can write the options. No, there is no options. I have written compute the exact value of this expression. I can wait a little bit for you. So you see that in this form, it seems that it is not a Pascal identity at all. And I agree with you, it is not. Yes, but you have to do one little trick, and then suddenly everything will work out. And the little trick I tell you, but then you will find it. The little trick is to do something with the first one. So by the way, what is this number without calculation? 2 choose 2. You have 2 people, you want to choose 2 of them. In how many ways you can do that? 1. Of course, you already hopefully know that n choose n is always 1. Okay, but of course, this and that or doesn't make any Pascal identity, because for the Pascal identity to work, the numbers on the bottom should differ by 1, but they don't differ by 1. And on the other hand, the numbers on top should be identical, but they are not identical. But now, because I told you that this is 1, can you tell me what to do now?
3 choose 3.
Yes, instead of 2, 2, you put 3 choose 3, because they are the same, yes? But how this will solve the problem? So first of all, I hope that you agree that I am allowed to remove this and put 3, 3, yes? Why? Because 3 choose 3 is 1, 2 choose 2 is also 1. So I am allowed to take this off and put this one here. And then you immediately, what happens, you see what happens. This one and that one is a Pascal identity. Yes, why? Because they are the same, but they differ by 1 unit. So I can combine this with that. What is the answer? I have to add 1 unit to the top number, which becomes 4. Between these two numbers, I choose the bigger one. That's 3. And then you see what's happening now. The story is now this one with the next one becomes a Pascal identity. Yes, so that's the idea. So what happens? This one with that one, the numbers are on top are the same. I add 1 unit to the number on top is 5. And then between these two, I choose the bigger one. It becomes 3. And of course, what is coming next? The next one is 5, 2. So you can just combine them one by one. Okay, can you predict if I continue this, what happens at the end?
100.
Yeah, because what is the last one will be what? 99, yes, and then 3. If I continue up to that point. And then I will have 99 choose 3, 99 choose 2. So if I combine them, what will happen? It becomes 103, yes? Is that right? So I don't know why I have asked exact value. The exact value, if you want to calculate this, is a little bit messy. So what should I write? I write 100 factorial, and then 3 factorial, and the difference between them 97 factorial. But I don't think it's a good idea to calculate it. So 99 times 96. 97 factorial is gone. So then I have 6. So this one to the 3, 2, and then this is 33. What?
98.
This one?
98.
Ah, yes, 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 thank you. Yes, and then divide by 2, it's 49. Yes? So then I don't know what to do. So this is 4,900, and then you multiply it by 33. So I don't know, is it correct I am doing it correctly? Because that is a little bit strange question that I asked to find the exact value. That would be probably enough. Yes, if I have 2 of them, it becomes 4, 3. If I have 3 of them, it becomes 5, 3. So then it becomes 103. So that's correct. So let us stop here. That is just a minor thing. You calculate this and multiply them, and then you will get a number. Okay, any questions? Okay, so mainly this combinatoric is finished. There is one binomial theorem, but when I check the questions in the book, there are some questions related to the probability, and there is also I don't know why they have chosen to put this in the exam, in the questions as level 3 problem, but this is not a level 3 problem. It's much harder than that. So let us try to understand that problem. That's also an interesting problem in its own right. I don't know, there are different ways to motivate it, but let me start motivating it using mathematics because it is clear what I am talking about. Some people call it combination with repetition, I don't like that name that much, but let us see how it goes. The question is this. For example, let me ask you this question. I have x plus y plus z. Let us say this is equal to 5. And then x, y, and z are non-negative integers. X, y, and z, non-negative integers. My question is that how many solutions you can imagine for this? For example, one solution is to choose x to be 5, y and z to be 0, yes? Because if I add them up, it becomes 5. Another scenario is that choose the middle one, 5. Another scenario is to choose this one, 5. But this is not the only one. These are not the only ones. For example, I can choose 4, 0, and 1. That is also the sum is 5. So my question is that let us write all of them down. How many of them are there? And we want to solve it in a way that if I increase the number of variables and I increase this number, this still works. This is one of the questions in the book. Not exactly in this form, in the general form, but this is the simplest one. Let us try to solve this problem. How this problem is related to combinatorics. Yes. No, the order matters actually, you see, because so far, how many solutions I have written? 4. Don't say this is the same as this one, because this means x is 5, y and z are 0. This means x and z are 0, but y is 5. And you know that in algebra equation, it matters. This is different answer to this. So order matters here. No, I was not talking about combination. I'm talking about combinatorics. So how can I use the power of combinatorics to solve this problem? It is not trivial at all. In statistical mechanics, this is called Bose-Einstein distribution. So when it carries a name, I don't know why they consider it a level 3 problem. But of course, it doesn't mean that you need the genius of Einstein to be able to answer this one. Yes. Now this problem, let me try to describe it for you. It's a very beautiful way of solving the problem. Let us say that I have 5 ones. Yeah, so can you erase this from your memory? I want to give you another problem. I give you 5 ones, yes, and I give you 4 zeros. Can you tell me in how many ways I can arrange them in which order matters? Forget about what I told you in the beginning. The problem is extremely simple and standard now. I want to tell you, I give you 5, I give you 5 ones and 2 zeros. Okay, and I ask you, in how many permutations are there? 1, 2, 3, 4, 5, 6, 7. I have 7 objects. I want to know how many permutations are there. Yes? This is a standard problem, yes? Because I want to talk about permutations, but some of them is repeated. So if none of them were repeated, I would write what? 7 factorial. But now I write 7 factorial and then divided by 5 times repetition of that, and then 2 times repetition of that. Okay? This is the answer. My claim is that the answer to this is the same. How can you find a connection between this? So that's a claim. This is not a hard problem. Hopefully, if you are coming with me, this is a matter of seconds to understand that is the number of permutations of these objects. But it is not at all clear why the number of permutations of these numbers is the same as the number of solutions to this equation. This is important if you can come up with a story. So why do you expect the number of ways that I can arrange 5 ones and 2 zeros has something to do with the number of solutions of this equation. So, and then to guide you, you might get a feeling why I chose 5 ones and 2 zeros. Or you want to tell the story? Okay. Yeah, the story is a little bit.
If you think of assigning each number, if you're adding them together, it's like.
So let me make your task a little bit easier. Let me write one arrangement for you from these. For example, one possible arrangement is 2 ones here, 1 0 here, 3 ones there, another 0 there. Do you agree? This is one of the possible ways that I can arrange these objects. Now my question is that if you want to think about the story, think about this story. How can, from this code, I can come up with a solution to that equation? So if you tell me how to do this, that it works all the time, then it means that you were able to establish a one-to-one correspondence between the arrangements of this code and the solutions to that equation. And if I can establish a one-to-one correspondence between two bag of things, then it means the number of items in one bag should be equal to the number of items in the other bag. Yes, that's the idea. So can you tell me this corresponds to which solution? So just tell me the solution.
That's not ready for this.
Okay. Yes?
X equals 2, y equals 3, and z equals
0,
0.
yes. So let me write this one, 2, 3, and 0. Yes? So then let me write another code here for you. 0, 0, 1, 1, 1, 1, 1, 5. So do you think if I write this, you see, it is like deciphering codes. Let us say that I send this code to someone, that person knows the rule, that person wants to decipher the code and find an answer to the equation. So you came up with the correct answer, okay? But can you tell me this code represents which solution to that equation?
0, 0, 5.
So you say 0, 0, 5. Okay. Okay, let me write another code. I will of course explain it, yes? So let me write another code. So let me put a 0 here, 2 ones here, another 0 here, and 3 ones there. So can you read the, if I give you this code, which solution do you show me? Anyone else? I want to see how many of you discovered the pattern.
2, 2, 1.
What?
2, 2, 1.
2, 2, you said 2, 2, 1. No. Yes? 0 to 3, yes. This is 0 to 3. Can you see the pattern now? This is the way that the person who established the one-to-one correspondence did it. Might be you are smart enough to find another pattern. It doesn't matter. I'm just describing the pattern they did. Okay? But do you see what's happening now? So I don't know, but let me write another one. So I write 1, 1, 1, 0, 0, 1, 1. Yes?
302.
302, yes. Yes? So let me do it the other way around. Now I will give you a solution. I want you to write me the code. Can you do that? Okay, so for example, let me, that one, 401. 401 corresponds to which code? Anyone else? Yes? 1, 1, 1, 1, 0. No, because we have two zeros. 0, 0, 1. Yes, that's correct. Yes. So can you now, do you see what is the correspondence? So if the people who have discovered the rule, they are able, whenever I tell this one, they can give me the solution. Whenever I give the solution, they can write me the code. So the point is, I want you to understand this. We haven't answered the question yet, let us say, but I want to convince you that the number of these codes and the number of the solutions to my problem are the same. So it doesn't matter if I count the number of solutions or I count the number of codes. This is an extremely powerful technique in combinatorics, and that's called, we discussed about that a little bit a while back, but this is called one-to-one correspondence. Okay, but what is the rule? The rule is that these zeros are separators. Yes, so you have two zeros, and then how many space you will have? One space here, one space there, and one space there. The number of ones on this is the answer to x. The number of ones between these two zeros is the number of y. The number for y and the number of zeros on number of ones on this space is the answer to z. That was the rule they used. And hopefully you agree there is a one-to-one correspondence between them. Okay, so the answer to this problem is extremely simple now. So if I ask you how many solutions are there, this is the answer. Yes or no? Is that clear? Okay, so if you understood what is going on, let me try to increase the variables at that number. Okay, so for example, let me write x plus y plus z plus t plus w. Yes, and then I would write here 15. Again, I want to restrict myself to non-negative integers. I ask you the same question. How many solutions to this equation do you think there is if I want to consider x, y, z, t, w non-negative integers only? So which kind of code you need now? So here, in this case, I chose 5 ones and 2 zeros. To solve this problem with the same method, how many ones do you think I need? How many zeros I need? Yes? Yes, 4 zeros. Yes, because I told you 4 zeros are enough. 4 zeros is acting as separators. Yes, 4 zeros will give me how many empty places? 5. And how many variables I have? 5. So I have to have one zero less than the number of variables, but the number of ones should be exactly equal to this number. Okay, so can you tell me how many non-negative integer solutions are there for this equation now? You told me how many ones you need? You need 15 ones. And how many zeros you need? 4. Okay, and then how many ways you can arrange them? How many objects I have? 19. But, sorry, I will write it as combination later. So I have 19 factorial here, and then 15 factorial because of this, and 4 factorial because of this. Yes, by the way, now you can write it as a combination. What is the combination? 19, you can choose 4, or if you want, you can write 19, choose 15, it doesn't matter. So the number of solutions to this equation is this, either that one or that one. Okay, so now are you ready to generalize it? So let us say that I have n variables. Yes, and then let us say that this number here is r. Of course, r is also a non-negative integer. And I want to have these variables to be non-negative integers. So can you predict in the form of combination what will I have? So again, how many ones I need, how many zeros I need for this solving this problem? The number of ones should be how many? R. The number of zeros should be n minus 1, because zeros are playing as the role of a separator. So what can I write here? R plus n minus 1, yes? Or n plus r minus 1. N is the number of, no, sorry. R is the number of ones, and n minus 1 is the number of zeros. So in total, I will have r plus n minus 1 objects. How many I want to choose? I can either write r, or I can write n minus 1. Yes? Is that right? So that is the number of ways that you can have these solutions. Is that understandable? So that was the content. I don't know which problem in the book. That's the level 3 problem in the part of combinations, but that is the idea for that problem. Is it clear? Okay, so now that I talked about one-to-one correspondence, I can give you another problem. That's also good. Of course, this is not finished. We will solve some more examples on this. So if I want to write it down, so the number of non-negative integer solutions to the equation x1 plus x2 plus up to xn is equal to r. R is also non-negative, R is integer, okay? Is equal to n plus r minus 1 and n minus 1. Or you can write n plus r minus 1 r. It depends on what you want to write. Okay, before finishing this problem, let me ask you one question. So for example, do you remember we had different models for distributing marbles in boxes? Okay, now let me give you this distribution problem. So I have identical marbles. How many of them should be there? So I have R identical marbles. So it doesn't matter for me. Of course, this is a hard philosophical point, yes? Identical means even if I have two identical billiard balls, in classical physics, in the universe that we are living, we can still distinguish between them, yes? But let us imagine, in combinatorics, be abstract. So when I say I have R identical marbles, it means that they are not distinguishable, okay? And by the way, you can keep track of them, but if you go outside the room and I replace them and you come back, you don't notice anything. So from this perspective, it is identical, yes? But if you are looking at this and I am changing it, might be you will be able to try. At this, you can make a film of it and then a slow motion and then keep track of which marble is going where. You know that in quantum mechanics, this is impossible. So you cannot do the same trick with electrons, for example. This is why electrons are all identical, and that's a mystery of our universe. So here we have n distinct boxes. Number 1, number 2, up to n. I don't know how much do you remember. These are very important models, and I tried. So let me review a little bit of these distribution models. And let us see how many of you remember this. So let me review from the beginning. If I have n marbles, when I label them, it means that they are different. And then I have n boxes. When I label them, it means that they are different. I want to distribute the marbles within these boxes. The constraint is that every box should receive exactly one marble. So this distribution, what is the answer to the number of ways I can do this distribution? N factorial. So this is a very standard one. Yes. Now let us say that I have n distinct marbles, but I have less number of boxes. Let us say R. So R is less than or equal to n. Now I want to distribute these marbles within the boxes, but the constraint is that every box should receive exactly one marble. So what is the answer to this distribution model? P and an R. Yes? There was another distribution problem whose answer was exactly P and an R. What was that? In this case, I have r this r different marbles. Again, r is less than n. This time I have n boxes, but the boxes are also distinct. Here, the number of marbles is more than the number of boxes, and each box should receive exactly one marble. Here, the number of marbles is less than the number of boxes. I want to distribute them here, but the constraint is that every box receives at most one marble. Because of course the number of marbles is less than the number of boxes. I cannot put at least one in any ground. So if I want to say that each one of these boxes either receives nothing or at most one, the answer to this distribution model is also Pn and R. Okay? And then we also had some other distribution models, which the answer to this is combination, not permutation. What was that? Do you remember? I have, for example, I have n identical marbles, so I don't label them. So they are identical, but the number of them is n. But how many boxes I have? I have one box here, two, and then I have r boxes. No, sorry, I think this is also no. Let me write them with label first. Okay, so this is number n, so I don't need to write n. But here I have r identical boxes. In how many ways I can distribute the marbles within the boxes with the same constraint? Every box should receive at exactly one. So you see this is similar to this, but the only difference is that I have removed the labels. Okay, the boxes are identical. So the answer to this problem is n choose R. Okay, and then there is something analog to this. What is that? This time I have R marbles. Okay, R marbles, but they are identical. But now I have n boxes that I can distinguish between them. But the point is that I want to distribute these marbles within the boxes so that every box receives at most one marble. The answer to this one is exactly this one. Yes? Okay, now let us come back here and solve this problem. This problem, you might think this is the same. Here, what was the constraint? Do you remember? I told you that I have R marbles identical. I want to distribute them here so that every box receives at most one marble. Yes? But now, let us solve this distribution model. I have R identical marbles. I want to distribute them within these n boxes, but there is no constraint. So for example, you can take all of them and put them in the first box. Yes? Or you can take 3 of them, put them in the first box, the rest of them in the second box, and nothing in the rest of the boxes. So this distribution model. So I want you to see, the first picture is the same as this one, but my distribution has changed. Here, I want to distribute it so that in every box, I receive at most one marble. But relax that condition. Distribute the marbles within the boxes in any way that you like. In how many ways I can do that?
Choose R.
No. So if you say n choose R, so it means that the way I distribute doesn't have any effect. So you see, yes, this is identical to this one. This is identical to this one. But here, I am not allowed to put 2 of them in one of them. So every box receives one or nothing in this case. But here, the first box can receive all of it. You know, this is a different distribution. So you take the marbles and just distribute them in the boxes in any way that you like. How do you solve this problem? It's completely related to this problem. This is why I want you to see the same problem from different perspectives, that you can have abstract models in your head. Yes.
But in that problem, I think, in the x plus y plus z equals 12, then you need like at least one marble in each box. You can't have
No,
empty
no,
boxes.
no.
Zero.
No, because might be the answer to one of the variables is zero.
What you say?
Because the variable, I erase that, but some of the variables could be zero in an equation.
Yeah, but then you have the marble that's labeled 0, and then you put it in that box.
No, so you're confused. That's nothing related to the label. Yes? So I don't understand. Are you answering the question or are you asking another question?
No, ask another question.
Okay, so don't keep it. Okay, don't confuse me. Yes? Yes? So the problem is this. I give you n distinct boxes. Sorry, yes, n distinct boxes, and I give you r identical marbles. Yes? And then I want to tell you, for example, you want to distribute them inside the boxes. So let us say that the boxes are big enough. And you don't have any constraint. For example, you can take all of them and put them in box 1. This is one distribution. I can take all of them and put them in the last. This is a different distribution because the boxes are labeled. If I put all of them in box 1, it is different from the case if I put all of them in box n, because you can see the difference. The boxes are labeled. But for example, you can take 2 of them, put it here, 3 of them here, and the rest of them in the last one. That is also one possibility. I should count it once more. First of all, do you understand the distribution problem now? Okay, we want to see how many ways we can do that. Yes?
It's n minus 1 plus r, choose r.
The same answer, you mean? Yes. The answer to this distribution problem is exactly this number that you see on the board. So this is why I told you I want you to feel it from 2 different perspectives. It is good. How can you defend yourself? Why this number should be exactly the same?
Because the boxes are like the variables, and then you have r.
No, if this is your story, that's a coincidence. There is a connection, but I don't agree with you 100%. You have to defend it better. Yes. No, what he said is more or less the same. But why it is related to the equation? Where do you see that equation? This is not just n variable. This is the answer to the number of solutions of an equation. Where do you see that equation here? You need to find a relation between this problem and that problem and convince me they are the same. They are 2 sides of the same coin, then I accept it from you. Because just because I have n boxes and then you see there are n variables, you see this answer is that. Are you ready to bet your life on it? That's important. Whenever you want to answer these questions, you need to consider it with your life, you know. So for example, can you interpret what is x1 here? So if you don't know, then you are doubting, yes? So what is x1? x1 is the number of marbles I put in box 1. Yes? x2 is the number of marbles I put in x2, in box 2. Okay? So what happens? x1, do I know what is x1? No. Do I know what is x2? If x2 is the number of marbles here? No. Because I don't know. You have to distribute it, then I know. But one thing is clear, even without you distributing it yet. What is that? x1. Let us say x1 is the number of marbles in box 1 after distribution is done. x2 is the number of marbles in box 2 after the distribution is done, and so forth. Do I know x1 before distribution? No. Do I know x2 before distribution? No. Do I know xn? No. But I know something. I know what? Okay, tell me more precisely. I know something, even though I don't know what is x1 before distribution, I don't know x2 before distribution, I don't know xn before distribution, but I know is supposed to be R. Yes, that was the constraint of this distribution. Yes, so this is why I don't know this, I don't know this, I don't know this. First of all, I know that the sum of them should be what? R. Because I told you I want to distribute all of them. Okay, and the other hand, is x1, x2 non-negative integer? Because this doesn't solve all problems. This solves only the problems where these numbers are non-negative integers. But that is clear. They are non-negative integers. Either there is nothing in the box, so that is 0, or there is some number of marbles there. The number of marbles is an integer. So that's why this problem is the same as that problem. Yes? So it doesn't matter how you do the distribution. One thing is clear. The sum of all of them is equal to R. So if I ask myself in how many ways I can distribute the marbles, it means in how many ways I can solve this equation. Do you agree with me or not? Yes or no? Yes or no? Okay, that's it. So you can see this problem from two perspectives. One from equation perspective point of view, and one from this perspective of distribution. And you see that when I draw the picture, this drawing is identical to this one. The answer to this is this, but the answer to this new distribution is one of them, whichever you like to. Okay, so but you need to understand what is the difference between distributions. Any questions? Do you know when the lesson finishes?
55.
Oh, 55. Okay. Okay, let me ask you one question here. The constraint was non-negative integers. Okay, let us make it natural numbers. Non-negative means 0 is acceptable, but let us say natural numbers start from 1. Okay, so let me ask you this question. So, for example, I give you x1 plus x2 plus x3 plus x4 is equal to, say, 9. Yes? If I ask you how many non-negative integer solutions are there, the answer is exactly according to the formula. What is the answer? You take this number and plus 9, 1 unit less, and then this number, 1 unit less. I am using this. You can, of course, use that one, doesn't matter. And if I ask you what the answer is, this becomes 12, and this becomes 3. So that's the answer. But some of the possibilities that might be one of them or two of them are zeros. For example, in this number, this is counted 9, 0, 0, 0. This is one of the ones that I have considered here, because non-negative means 0 is acceptable. But let us now say that no, I don't want to have zeros. I want to have at least 1. Then how do you solve the problem? You see, this model is better here. Okay, so let us say how many marbles you have? 9. How many boxes you have? 4. So imagine you have 9 identical marbles, but you have 4 distinct boxes. But now you want to do the distribution as before, but this time you are not allowed to do what? To leave one of them empty. Yes, that's exactly the same problem. In the previous case, I was allowed to leave one or more of them empty. But when I say one of them is left empty, it means x corresponding to that box is 0, which is now not acceptable because of the new problem. This is why having this as a model in the back of head is good for answering some of these questions. So let us say that I give you 9 marbles, and I give you 4 boxes, and I tell you to distribute the marbles in the boxes, but you are not allowed to keep one of them empty. Yes? So what do you do in general? Now be careful about this. Is not possible that you don't know it. Let us ask the question in this way. You have 4 kids, and you have 9 candies. Okay? If you give all candies to the one of the babies, they will actually start complaining. Okay? So now I will say, okay, let us distribute the candies among the people and among the babies in a way that at least everyone receives at least one. So what do you do first? Yes.
Give one candy.
Yeah, I give one candy to each one of them, and then when they are busy eating, I put the other candies to the people I like, something like that. I mean, you can come up with a story. So that's exactly the same thing we do. So I have 9 marbles, I have 4 boxes. So what I do, I first take one marble to put it in the box 1, another marble to put 2, and then how many marbles will be left to me? 5. And I will still distribute it among 4 boxes. So this problem, so that every one of them should be at least 1, means it reduces the number of marbles. The boxes are the same, but the number of marbles will be 5. So it is as if I am distributing 5 marbles within the boxes with the previous condition. So what happens? So you can say that, okay, x1 plus x2. Well, of course, this x1 is not that x1. If you don't mind, let me write capital x1, x2, x3 plus x4, and then I would write it what? 5. And I don't, so I consider this problem. And the problem is exactly on the board. This number plus that number minus 1, and then what? 4 minus 1. So the answer to this problem is 8, 3. So this is the number of non-negative integer solutions. This is the number of natural solutions. Yes? Is that right? So this is why this is good to think about this distribution model. Yes, for example, let us say that how many solutions are there so that x1 is at least 1, x2 is at least 2. So you see, you can immediately solve this problem as well. So you see, I ask you the same question. How many non-negative integer solutions are there? But then I put 2 constraints for you. I would say that this is at least 1. The next one is at least 2. So how do you solve the problem? Again, so how many boxes you consider again? 4 boxes. Box number 1, number 2, number 3, number 4. But now you know that you have 2 constraints. The first box should receive at least 1. The second box should receive at least 2. So let us get rid of them first. What do? I take one of the marbles that I have 9 marbles. I take one of them and put it here. And I take 2 of them and put it here. So now I am not worried about my constraints. So how many boxes are there? I can ignore them in my memory. How many boxes are there? Still 4. But how many marbles are left? 6. And then I distribute 6 marbles within the boxes with the previous constraint. Yes? So what is the answer then? So this number instead of 9 now becomes 6. So then I would write 4 plus 6 minus 1. And then I would write 4 minus 1. So it is 9, 3. So this abstract model, to have it in the back of your head, is actually good. Yes. For example, one of the famous problems here is this. So you go to a restaurant, and then there are 4 types of foods, and then you are 5 people or 6 people. So let us fix it. You go to a restaurant. The restaurant has 4 types of foods. So 1 meat, 1 chicken, 1 fish, I don't know, 1 vegetarian, okay? So, and then you are 7 people. So in how many ways people can order the food? What are all possibilities of the ordered foods? Yes, so I have 4 types of foods. And we are 7 people. We go together to a restaurant. and we start ordering. We don't care about others, we just order, yes? And then the problem is that how many possibilities are there for the restaurant to see what is ordered? I want you to understand this problem is exactly the same problem, but you need to find a connection. So here we are 7 people, yes? How do you establish a connection? Because this is a different problem, but this is the good thing about these abstract models are this. Both of them are called them abstract. For me, sometimes working with equations is easier to work than boxes and things like that. So this is an abstract model. This is also an abstract model. It doesn't matter which one is suitable for you. As soon as you establish a connection between the problem given and one of these models, you already know the answer because the answers are on the board. Okay, so how do you want to interpret that?
You can interpret it as x1 being how many people ordered the first dish, x2 how many
Yes.
people ordered the second.
Yes, is that right? So I would say that x1, after ordering is finished, let us say x1 is the number of type 1 food ordered. Yes? And x2 be the number of second type ordered. And x3 be the number of third type ordered. And x4 be the number of fourth type ordered. Yes? And of course, we assume that no one is so hungry to order 2 foods. Okay, I should tell these things before, of course. So I don't know how many first kind food is ordered. I don't know how many second type food is ordered. But if the order is finished, assuming the ordinary conditions, one thing I know any one of them is a non-negative integer. Yes, for example, if this is the chicken one, might be no one is liking chicken, so not x1 will be 0. But it is clear x1, x2, x3, x4 are non-negative integers. And one thing is also clear. I know the sum is what? Is the number of people, assuming that everyone orders exactly one food. Yes? Okay, so this problem is stated differently, but that is this model or that model in a way that you like it. So you already know the answer. So the answer becomes 4 plus 7 minus 1, 4 minus 1, and then you can write it. Yes?
I'm a bit confused because previously you said that n should always be bigger than r, right? But here n is...
No. N, no, I didn't tell n and r. I told you whatever you see on top is bigger than what you see on the bottom. Yes? But in this problem, you see this on top. These n and r are not the n and r that I use for the standard one. Yes? Yes, you are right. But still, I am following the same rule. This number is definitely bigger than this one because there is one r extra there. Yes? Any questions now? Is that clear? Okay, let me give you another question. By the way, now that we have distributions on the board, let me do final distribution. Might be that's also a good distribution to be on the board. So let me add it now. So what do you think will happen if I have this scenario? So here, I want to make it identical to them. So here, this time, let us consider the so I have 1, 2, up to n marbles, but then I have r boxes. let me see. I have R boxes. There should be another distribution as well. So let me think about another distribution. I want to write a problem for you here, and I want you to think about that. I will think about this. Okay, so just be independent. I'm not saying that try to force yourself to solve the problem in this way, any way that you like it. I'm not even sure that this is related, but that's a good problem, at least especially for the one-to-one correspondence. So let us say that I have this checkerboard of roads. Okay, so let us consider that these are roads, something like that. So this is completely organized, but I cannot draw it precisely well here. Okay, and then you see that you have an ant here, so let us call it ant. Have you see the animation ant Z? Yes. So let us consider that this is ant Z, and then this is the grandma for this ant Z, and this is supposed to go and pay a visit to her grandma. And then there are two possible moves for this ant at each step, either 1 unit to the right or 1 unit up. Okay, for example, this is one possible way that this ant can choose to reach to here. For example, this one, this one, this one, this one. Something like this. I either go to the right or up. I'm not allowed to come down or go to the left. This is one path that takes the ant to the grandma. Okay? I want to count all possible roads, all possible paths or routes that this can routes, yes, that this ant can take to reach the grandma. I call them different if they at least differ by one step. Yes, for example, might be the other scenario is that you go here, 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 but you go here and there. Most of the dotted line is the same as the green line, but you consider them different because at least they differ at some point. Okay, so I want to count all possible routes that the ant can take to reach the grandma. Okay, you think about this problem, I think about what I wanted to say about this distribution. Any ideas? Yes?
15 factorial divided by 10 factorial 5 factorial.
I didn't count them, yes, but I think you are right. So what was your idea? So you are telling that no matter how the ant is supposed to reach there, because 1, 2, 3, 4, 5, 6, 7, 8, 9, that ant should go 9 units to the right, no matter in which way it wants to reach there. 9 units to the right, and how many units upward? 1, 2, 3, 4, 5, 6. So up 6. Yes. And then that is just the arrangement of R and U's. So that's why I'm saying one-to-one correspondence is extremely good. For example, can I code this green with R and U? Yes, because what is this? It's RR, 2 rights and 2 U's, and then 3 R's, and then 1 U, and then 3 R's, and then 1 U, 1 R, and 2 U's. This is the code for the green line. Yes? Is that right? So what is the code of the orange line? It is R, R, U, U, R, 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 and then U, R, 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 and then U, and then U, U, and then R. It's a different code. So this code is the orange line. So I hope that you agree there is a one-to-one. For example, if I write another code, you can find the route, yes? You can find the path. Is that right? So there is a one-to-one correspondence between the routes and the paths and the codes. So instead of counting the roads, you can count the codes. Yes, that's the one-to-one correspondence again. But is counting the codes hard? No, that's a standard model, yes? How many objects I have? 15. But some of them are repeated. 9R is repeated, 6U is repeated. So that's the answer. So this is a very powerful tool in your hand, yes? Okay, now let us go back here, what I wanted to say and finish this. Now, let us say that I have n marbles and k boxes. I intentionally wrote k because of the question you asked. So here I don't mean k is bigger than n or n is bigger than k. It could be in any way. But I have n distinct marbles and k distinct boxes. The number of marbles can be more than the number of boxes or the other way around. Okay, for some, of course, with some limitations. Okay, now the question is that in how many ways I can distribute the marbles inside the boxes? Any way that you like. For example, you can take all of them and put them here. You can take two of them, put them here, but it matters which one you put. Because if you put marble 1 here, marble 2 here, the rest of them here is different from putting marble 2 here, marble 1 here, the rest of them there. Yes? Is that right? So how can you solve this distribution problem? Is the question clear? So these are distinct, these are distinct. I want to do this distribution. I don't have any constraints. I can distribute them in any way that I like. Yes.
N plus k minus 1 choose n.
No, this is a much simpler problem. In principle, I could have asked this question in the first session of combinatorics. So you see, still combinatorics is hard. Okay, let me break this stage. This act, you see this, I could have asked this problem in the first session. I would say that the stage number 1 is assigning a box to 1. Stage number 2 is assigning a box to 2. You see, it was simple. So that's why I'm saying telling those stories is very important. So can you tell me, by this kind of constraint that I told you, how many choices I have for the first marble? Okay. Now let us say that I choose one of them and put that there. Now I want to put 2 there. How many choices I have for 2? No, because I told you k minus 1 is that I'm not allowed to put it there. But I told you distribute it in any way that you like. So what do you say? Again k. The next one is again k. And then when I reach the last one is again k. So what's the answer? K to the power of n. So you see, you have a lot of experience in combinatorics, but there's still some problem. It was actually a product principle. So you shouldn't get confused, okay? So that's why I'm saying, whenever you get confused, you have to be able to go back to the main principles and try to solve the problem from there. It's just a this is the product rule. Not product rule, what was called that? Product principle, yes. Is that right? Okay, we have 2 minutes. Okay, so let us say that this ant is supposed to go here, but he wants to also visit a friend here and then go and visit the grandma. So how many ways that ant can choose the path, the road? Yes? So here. So this here, in the first scenario, the ant can go from here, completely ignore this person. But now let us say, no, he wants to pay a visit here and then go and visit the grandma. In how many ways it can do that? Yes? Yeah, so you say that stage 1 is going from here to here, and then stage 2 is going from here to there. For this one to here, what is the code? 2 R's and 2 U's. So it becomes 4 factorial divided by 2 factorial, 2 factorial. Now this ant is here. Independent of how the ant reached there, from here to here, that's exactly another problem of this type. But how many R's I need? 1, 2, 3, 4, 5, 6, 7. And how many u's? 4. So it becomes 11 factorial, 7 factorial, 4 factorial. What should I do with these numbers? Multiply. Okay, in how many ways the ant can go there avoiding this person? This is the number of ways that this ant pay a visit here, but this time he wants to avoid. Let us say that he wants to actually introduce his fiancée to grandma, but then realize that the X is there. It's X, so he wants to avoid. Something like that. The stories are nice, you can remember them, yes. In how many ways you can do this? Yes. What? No. I don't know if you calculate it so fast that numbers coincidentally are the same, but technically probably not. How you calculate
You
that?
take that number minus the.
Yes, exactly. So the total number of ways that you can go from A to R is this. So this is considering a visit here or not a visit here. But the number of ways that you go here and visit is this number. So the answer to this new problem is this number minus the whole number here. Yes? Is that right? So there is one part of this left. I will solve some problems from the book related to probabilities. Okay, because I don't know, have you studied probability in Math 1C or not?
We did, but we didn't have a test.
Okay, so in Math 1C there are some, I will just give you a little bit of probability. Another part of probability I will teach you in Math 4. That is using integrals to calculate probabilities. But these probabilities we are facing here is a very simple ones. I will tell, so more or less we need 2 sessions to finalize this. And the next chapter is not related to discrete mathematics at all. So the nature of the next chapter will be very similar to Math 4. That's called differential equations. I don't know, for some reason they eliminated the graph theory, which is discrete mathematics, and then added something to differential equations. Any questions? Thank you.